Okay, I didn't put the video of the previous class. I will upload the video as well. So I just want to I will tell you that I didn't upload that. But this is from the previous semester I taught. So lecture 1 to 15, I was covering more process for system calls. So we will go to early memory system and memory management once we complete scheduling, I think. And then 15 to 30, I covered, virtual memory, MMU, the threads and P threads, PC booting, user versus kernel threads, inter-process communication, synchronization, software solution for critical section, bakery algorithm, hardware locks, mutexes, semaphore, introduction to mutual exclusion, strict alteration, producer-consumer problem, Peterson algorithm, and binary semaphores. So I covered those topics. So it was vast amount of topic I covered because I didn't have a constraint of time because it was asynchronous. So whatever I can cover, I covered. So binary semaphore, dynamic philosopher's problems, deadlock, dealing with deadlock, Banker's algorithm, CPU scheduling, priority-based CPU scheduling, multiprocessor scheduling, scheduling in Linux, completely fair scheduling, and finally, I covered operating system security on one lecture, information flow policy, buffer flow. So this, but I didn't cover file system. So file system I covered. This was the first time I taught file system and operating system course. Okay, so there are plenty. Book is plenty vast, and it can go over 1 year also. I can discuss real-time systems itself is going to be, and concurrency itself is a separate course. Real-time system scheduling itself is separate course. So here I didn't talk about real-time scheduling algorithms. So it varies semester by semester, but if you can understand the basics, you can follow this. Anyway, I'll put this. What I will do is that I will upload these scheduling whatever I discussed, lecture 36, 37, 38, 39, 40. I'll put that from the previous semester, so you can watch that as well. Okay. So, and you can definitely, when you can follow this class, this will be easy to watch as well. Okay. All right. Is that clear? So, and every time I also want to update my knowledge. So I want to cover different topics. I don't repeat my stuff. Yeah, especially in computer graphics course, I go and experiment with different things. So let's come to this class today. So we were talking about, okay, and what else I want to talk. So scheduling, is that clear? We are dealing with scheduling and discrete event simulator. And remember that when you are developing a simulator, only the process is we are simulating, and then we are simulating it. But actual logic, the same logic will be writing when you implement, replace the operating system code. There is something called as, I forgot the name of the operating system. Operating system. So it's also again developed by Tannenbaum, I guess. So you can this is open source again. So if you want to try your scheduling algorithms that you're proposing, you can try. This is going to be again, this is the next step. First you do the simulation. Once you do the simulation, and you can run your algorithm and test in actually in real time, because the process we are creating is a fake process. It's not actually a real process. Is that right? So we are not creating a real process. But when you go for Minix operating system, we'll be dealing with a real process. You're getting that and going to schedule them. So whatever the logic you're writing for priority queue or queue, whatever it is, same logic will be there, right? Logic or data structure is not going to change. Maybe that Minix operating system may not have priority queues. In that case, you have to use ordinary queues, right? But otherwise, the logic is going to be the same. But first thing is to know the simulation. First write your simulator, and then next step is, and like for this operating system Minix, we cannot do, we cannot implement. If you, unless until you work in Microsoft, we cannot do anything with Microsoft operating system. Is that clear? So this one you can do. So whatever the logic we are writing for shortest job first is applies to, so logic you are writing is, you can write in Minix and test your algorithm. Okay. So the process is actually fake. Fake process means it's not an actual process. We create a process generation file with arrival time, bus time, etc. And then we schedule this process, and we are writing a discrete event simulator, right? And here I think I have the link for discrete event simulator. So let me just, I don't know where exactly talk about discrete. So discrete event simulation can be also called as like event-based simulation or also time-stepped simulation. So discrete event simulator are classified mainly into two parts. One is time-stepped, and another is event-based simulation. So whatever simulator we are writing is actually event-based simulator. What is the events? Basically, arrival of a process into the RAM is nothing but an event. Completion of a process and moving that process from the RAM to the hard disk is basically an event. So you can classify this into discrete event simulation into event-based simulation as well as time-step simulation. We are not using time-step simulation. In time-step simulation, you increment time in discrete steps. So that is called as time-step simulation. So one example, I don't know, this is the, I just copied this. I just taught previously. I just want to, I showed you that that this time-step simulation has some problems. You can notice the problems in Blender. I think was about, I think you cannot listen to the recordings. Sorry, you cannot listen to this what I'm talking, but this is not the one I'm talking, but I'm talking. So this was, I was also covering how to do visual effects for my students, how to remove the green screen. I was talking about that, and then I but what I was trying to do is this one. So this one I was trying to show the student the work. This is particle space simulation. I think where is the problem? I exactly want to show the problem, right? So here there is this is also a time step simulation. This one I just I don't know where exactly the problem. Maybe I have to note the time step. But what I want to tell in this particular simulation, this is again discrete simulation. It's not loading for something. What I want to tell you is that here, you know, the particles are emitted from the man I placed here. There's a OBJ model. There's a plate here. So this particle has to detect the basically you know, there should just be a plane intersection, but the test is done every time, discrete time limits. So what happens is that the particles here, they don't stop exactly it will go beneath the basically it will go beneath the plane. So that is an example. Exact time step I spoke to the students but that time step simulation. The particles will penetrate and only few particles are able to be there. Not few, most particles will capture the plane, but few particles will penetrate into the plane and fall down. Because that is what is the time step simulation is, right? So we are not dealing with time step simulation for our case. So this is different thing. And I don't exactly, I'll show you that it is not also going very fast, but I want to explain what is this time step simulation here, right? So I don't know, it's not moving fast. Exact time step I will follow. Yeah, but I know I will show you next time. It's very fast, very slow. I will download this video, and this one I also, this one is again VFX part. So this green screen is a VFX part I taught in Blender. That is also very nice. You can, I mean, I think I'll be offering this course in fall of 2021. Okay, so if students were interested, see here, I just replaced the green screen with the background. So he's watching from the bridge, right? So this one I again did with Blender. So these are node-based things. So I did this. So this is also very interesting. You can see in movies. This is okay. So I hope discrete simulation is discrete simulation is classified into event-based and time step simulation. Okay, we are not using time step, we are using event based simulation. What is an event? Occurrence of something, arrival of a process into the RAM is an event, completion of a process is an event, and taking the, you know, preempting a process is also an event. So these things are classified as event based simulator. Okay, so let me start from the point where I left, and I want to cover a few more scheduling algorithms. I hope we can start implementing. By this time you should know how to generate process. So what I was trying to, okay, this is again not my course. This is, I was discussing full adder circuit with my computer organization students. Most of them got lost with full adder. I know it's difficult to do the first time full adder, you know, or parity generator, the circuit. So, and I was trying to explain them and all this stuff, but they got carried away with this thing, but that is not, this class is about here. So let's move the board here. Okay, so what I want to say is that so there was see uh, we have CPU time, or it is also called as execution time, burst time, and this is process coming ID, right? So this 1 and 10 and then 10 seconds or whatever. So I gave the example before, was this right? What was the example I gave to you for shortest job first and shortest job? I gave this example, right? And I will go over this again. And do you remember what is the logic I told? Because here the shortest job you're serving first, and what is the problem with this algorithm? It leads to starvation because of the jobs keep coming from the hard disk, and some jobs, it's called an indefinite wait, and we don't know when that process will get the. Okay, this is arrival time. This one I wrote is arrival time, right? This is an arrival time. Arrival time. So this is arrival time, and we have 5 process, and we develop the Gantt chart for it. So 3, 2, 3. So this is your file going to be looking like in the process generation file. You're going to get this, and then you have to read this file into a process control block. We have to, I discussed about the data structure last class. So you read these elements, don't put in a separate queue. So you create a data structure called as process control block that is hold all this information, right? And then what you are going to do is put into the, we are going to read the file and put into the process control block. And we have, I told that we can, so all this information are stored in, this is an object, all this information are stored in PCB. And then we have this collection of objects. I told we can design a priority queue here. And this priority queue, you can have ordinary queue also, or priority queue, whatever. So I think priority queue is fast. In Java, it is there. So what is the priority queue? Initially from our simulation will start from, because if you see here, the first process arrives at time 2 units. Is that right? It arrives at time 2 units. So what the CPU is going to do? So scheduler has nothing to do, because if you have priority queue, this priority queue is basically empty. But here, this queue actually, it's for our, you can call as, I don't know what you want to call. This queue actually is for our, for implementation. Actually, we are doing it, and because we need to store this information somewhere, all this process. And this queue, what I want to call, this is like a queue of processes or something. You can call whatever queue you want to call, and queue of process. So what happened is that you put all this this thing, and here you whatever the queue you call, I don't know exactly what you want to call. So I read from the file and put it in the process. I will read as an object process control block. I'll put in the queue of process, basically. Is that right? And this queue is again a priority queue, because you can sort by the arrival time of this queue. Can sort by arrival time, right? This queue is priority queue again. Name of the queue is this is, you can say, ready priority queue. So this is ready priority queue, and this is always in the RAM. Okay, and when you parse this file, you are going to put everything in the, basically in this queue. Basically arrival time is, basically you will be putting PID 1, right? So P1, because that one arrived first, P2, P3. And I'm talking about this projects, how to implement that as a project. Okay, this is I'm trying to use this is shortest job first. So how many processes are there? So we put, and they are in the increasing order of the arrival time. So I don't have to sort. I'm just putting like P5. But priority queue always does order. So, you know, based on the arrival times, here you can have an arrival time. And this queue we are doing for the simulator purpose, but actually there is no queue like this in the when you implement what we, because the ready queue is there in the this thing. See, this process is not yet arrived, right? So we just simulate that this process arrives in the, what do you mean by arrival? The process comes from the hard disk to the RAM. The point at which the process gets transferred from the hard disk to the RAM is known as arrival time. And this arrival time we are simulating, right? And this is basically the process of this didn't arrive yet. So this still process is, this is not in the RAM. Actually, for implementation purpose, we are having this queue basically. Is that clear? So the priority queue, the ready priority queue. So you can have ready queue or ready priority queue. This is arranged by, sorted by, basically how it should be sorted. Can you tell me how it should be sorted? The priority queue for the ready queue. Ready queue, how it should? Yes, very good. Shortest time first, right? So you can arrange this thing. That means that what is, so let us talk here. So no process has arrived, the ready queue is empty. So if the schedule, if ready queue is empty, let me just write that if RQ is empty, ready queue. So ready queue means ready queue is also a priority queue. If ready queue is empty, then what you are going to do is there is something called a simulation clock, right? Simulation clock. Simulation clock is the clock which is not real clock. It is called simulation clock, not the physical clock. You initialize that variable to 0. Simulation clock will be 0, right? To start with, begin with, the simulation clock is going to be 0. Then what you're going to do this, if ready queue is going to be empty, then you're going to check this queue, which is the queue of process. And then we are going to, because if I see the Gantt chart, if I draw the Gantt chart, see, I'm talking about the implementation for your project, guys. So, and so please watch this carefully. So simulation clock is 0, but when this first process is arriving, at what time unit? What time unit? I just, oh my God, this is a problem. I don't know how to zoom out. Does anyone know how to zoom out? Yeah, zoom in. Yes, zoom. Usually it's control plus, but yeah, now it came back anyway. Okay, so during the two units, when this process is arriving, 2, and that means the process is not arrived to the RAM yet. It is still in the still in the hard disk. Is that right? So what does our simulation has to do? Because it is waiting for an event. I said it's event-based simulator. So it is going to look at this queue, right? And it is going to update my simulation clock to 2 basically, because we don't have 2, we are not doing anything. So simulation clock should be if ready queue is empty, then examine I'm just writing the pseudo code. You might examine the whatever the queue, let me call as QP or whatever. So this queue is called as QP of process, whatever. Example QP, QP of examine QP, and to select the process, from the priority queue, from the QP to select. So what you're essentially doing is that you're putting that, because this priority queue is empty, right? You're pulling this process out and putting that process into this queue, which is called as this was going to be coming from here to here. So if the ready queue is empty, then you're going to examine the other queue and remove from the front of the queue, because it is a priority queue. This is ordered by the arrival times. See, there is no need to use priority queue. You can use normal queue. Then you have to search the entire queue, right? So if you say that priority queue, we can always remove from the what do you call that? Is called top. What is that operation called? I forgot. When you remove from the priority queue. NQ and DQ. Yes, thank you very much. So we can NQ basically from that, and we can perform NQ. Basically, it's removing from the head here, and we will take this process and put back to the ready queue. And then what we are going to do, simulation clock has reached here. And the simulation clock has been updated, because when you move from here to here, the simulation clock basically becomes 0, will become 2, right? And then what happens is that then we have a process from the ready queue. Is that right? And this is the shortest job first. So what we have to do, we really don't have to go back to this queue and do anything, because this process is going to run from 2 to until what time? 4, right? So basically, again, you select the process, move this process. See, it is not one process. Again, remember that I'm not removing one process, because it can be several processes which are running at the same time. So we'll pull down we remove all the process that arrived at that particular second and put into what? The ready queue. That ready queue is there. Ready queue is maintained in the RAM. Okay, so ready queue is there. So you have to remove all these process which have arrived at time 0 and put at, not at time 0, whatever it is. They arrive at the same time, right? So let's say you and I forgot your name. What's that?
Oh, yeah, lateral, the first student in the class, right? Yeah, laterals. Okay, lateral and I'm sorry, today I'm not getting any. Uh, okay, yeah, you both are at the same time.
So we'll be both moved into the ready queue. But who I'm going to select from the ready queue basically? No, whoever execution time is less, right? It's not first in the list because this queue is yeah, okay, I got you. Okay. But what I'm telling is that in this particular case, we move only one process. But if for example, let us say P2 also arrived at here, I will change the P2 also arrived at 2 time units. I just change it. So then we'll move two process from the ready queue to the prayer this thing. Among these two process, I will check which process has the least execution time. Suppose in this example, let us change this example. So P1 and P2, and again, this is sorted by what? Bus times or execution time. This is also a priority queue. So P1 and P2 arrived at the same time, 2 units or 2 seconds or 2 nanoseconds, whatever you want to call. They are the same second. So I remove these two process, basically P1 and P2 from this. I don't know exactly what to call this queue. We can call queue of processes or or what you want to call. You can have some meaningful name. Can you suggest some name? Okay, arrival time queue. Okay, arrival time queue. Whatever you want to call, meaningful name, that should be good. Okay. So you are when the CPU is idle basically, or when the ready queue is actually empty, then we are going to remove all the process from this queue to this queue, and then we are going to schedule it, right? So this is ordered by by priority. How we are ordering? You are ordering by what? Bus times. Is that right? So bus time. So technically what happens is that this will be like this: P2 will be here and P1 will be here because this is a priority queue set, right? So P2 will be in the front. So our simulation clock then will take P2, will remove this element, and then update the simulation clock will become it was 2 before, right? And now it will be 2 plus P1 dot burst time. Let's say we have data structure in that we call P1 dot burst time. So because this is again, we don't have to check. This is shortest job first. So whichever jobs has the highest priority, if it is given the CPU, it will not be taken back, right? Then the logic is that we have to move our simulation clock to the until the execution time of that process. Think about what you will do with the kind of shortest remaining time next, which I'm going to talk about. But are you able to understand my logic here? So we maintain 2 queues in your algorithm. When you write the code, you maintain 2 queues, and if no process has arrived or if the ready queue is empty, then move all the process which has arrived at particular time. So they might be tied. So you have to move all the process, move to the ready queue. Ready queue itself is sorted by what? Arrival times. Is that clear? So sorry, ready queue is not sorted by arrival times, it's sorted by the execution time, right? Arrival queue is sorted by the arrival time, but this queue is sorted by the burst times or CPU execution time. Then we can remove from the front of the queue and we can move our simulation clock from before it was simulation clock was till 2, it was not doing anything, right? Then it was scheduling from 2. This is P2 is now we are going to update the simulation clock. So P2 is I think P2 requires 2 time units. So 2 to 4, P2 will be given the process. Then again, you have to go and check this queue, right? Once this is till this point, you don't really have to check. Then again, you have to go and check this queue to see if there is any other process which has arrived. If there's any process which has arrived, then we have to move that process from this queue to this queue, right? So you have to write the logic. So once you update the simulation clock, you again go and check that queue to see that between this time lapse, between 2 to 4, any process has arrived. Yes, of course, P3 has arrived. So we'll remove P3 and put in this queue. And of course, this P2 is completed execution. It is no longer in this queue. You can remove it completely. And we will calculate all the statistics, arrival time, completion time. We can subtract and everything and put in the task control block. We will put that in the, you can have that. You can store that information when it arrives, when it completed, etc. Turnover time, everything, right? You can calculate. Is that clear? So similarly, you have to keep doing it. Shortest job first is very easy to implement, to be honest. If we can implement shortest job first, shortest remaining time next, modify small logic, implement that. This is what is discrete event simulation, nothing complex here. We are moving the simulation clock ahead, right? That's why it is event-based simulation. I'm not like checking every time unit. I'm not checking every 1 millisecond. I'm not checking the process array or not. We are based on event. We are just checking it. So this is called an event-based discrete simulation, event-based discrete events, or discrete event simulator, whatever called event-based discrete simulator, right? This is clear. This is how you do this logic. You do this logic until you complete all the 5 process here. Very simple to implement. Honestly speaking, don't worry too much. If you need help, I will help you, but you need to write comparator. I will show you. See, we always talk about different algorithms, but we really don't care. What we really don't care is that how to implement that. Implementation will give you lot of ideas and it will lead to lot of research. You will question a lot. Then you will propose your own algorithm, right? When you implement only, just reading the textbook, it doesn't, you won't implement anything. When you actually implement it, your new ideas will be born. Then why you are doing in that way, maybe you may be a better way, you will get more ideas. That's how it leads to publication, right? So initially you have to implement. That's very important. Anyway, I will show my file explorer. I will show this. How about the Zoom students? Are you able to follow me? Nadisa, you don't have any questions? Or Steven, you don't have questions? And who else is there? Aman?
No, not yet.
Not yet, right?
I think
So
it's
clear.
clear, yeah.
Yeah, because this is very important, and don't do the project at the last moment. Don't do it. You start next week. What week? Next week is basically holidays, right? So please start working on that. And actually, if you go to my tree drive, I'll show this. Actually, then I appended, and this is CPU scheduling. I think this is and source code. My skate simulator and source code. And I didn't have shortest job algorithm, but I have first come first served. Maybe that is the easiest algorithm for you. So I think I'll open in Visual Studio. That is matter. So and this is basically the whole code. Actually, this is the is very easy. Set begin time and calculate FCS. So this is my whole code actually, to be honest. But only thing you should know that how to write constructor, and this constructor is receiving nothing but an array of type PCB, right? So this is the whole thing. So get arrival time is not complicated at all. And see how I'm calculating this timeline. So this is a process control block. This process, I don't know why -n I put, but it depends upon the logic. So get arrival time, everything, and I'm updating this logic I told, only I'm implementing it here. And scheduler, actually it's going to select which algorithm I'm going to use. This is like a common thing I just developed, which is going to be saying again, it's all statistic information. I'm having all statistic information, and scheduler is going to calculate this, and we can select which scheduling algorithm we want to use, right? So I didn't select here, I think, but yeah, long time before. Anyway, I wrote this code, but this is going to scheduler, and then it uses different algorithm. I think scheduler, I actually scheduler will do the statistics for me. I think the main is the one I was doing, I guess. So it was reading and putting everything into the JSON file, and see, this is all parsing of files. So don't worry that this is all complicated. This is how parsing. And see here I just said, I can, this is from the command line. If objects dot equals rs1 is going to be, it's like command line. I argued if it's first come first serve, then it's going to use that round robin algorithm. Actually, it is using the first come first serve, else it's going to be a round robin. I'm checking which algorithm I want to use. I will select round robin and do the scheduling. So basically, so right now, don't think too much complex. Whatever I told you, do that first. Shortest job first. Okay, implement the shortest job first. Everyone will have different implementation, and of course, if two implementation are same, because two people cannot. So this is another problem that I find with undergrad students, or back at University of Calgary, was a teaching assistant, or UNBC. Students replace the variable name, find, and they get the code from other person, and instead of round robin, they will find and replace and everything. And of course, I can find if two person cannot think the same way. Your code, my code cannot match. I'm telling you. because when I write the code, okay, I find something better than this, then I do that, right? So no two codes can be same. So you cannot give your project work to other person and then submit it, because I can say that read your code and find that who is doing what. And of course I told I can also check other ways to find out, right? And again, there are some people algorithms to detect plagiarism software. Again, they use algorithms to detect whether two things are same or not, right? That's also interesting topic if you want to do research on that. Okay. And D2 Health has such facility already. But anyway, same thing. This year, I want to show that this is a CAN scheduling I did for my work with Dr. Kim, Professor Kim. I hope you know Kim, right? Have you taken courses with Kim? Haklin Kim? No? No, I am the one biology and computer science. Was it? I don't know who was that, but this is Professor Haklin Kim. He teaches operating system course usually. No, I grabbed the course from him actually. So usually teaches operating. Now he's teaching artificial intelligence, right? So anyway, we wrote the paper, and for that paper I wrote. So that's why I just put Kim Can, his name, CAN simulator. So I used his name. I don't know what to call that scheduler. So I put Kim. So this is a comparator I use. This is very easy again. You learn comparator is very easy. I mean, you see here actually that compare. So I use overriding this method compare. So if T1 is taking two control process two objects, T1 is actually an object of type TCE. Because I said task control block, you can call process control block or task control block at T2. So I'm just comparing, and this, if I can write this comparison, because I'm overriding this method, because this method is already there in the comparator, and I'm telling that I'm comparing this arrival time and then putting that into the sorting. We need a comparator for penalty. See, if you don't want to use comparators, all these things, you can use your own way. You can put a normal view, scan the entire view, and then find a job with the least arrival time and move that process into this view. And then again, you scan the view and then find the process with the least arrival time and then increment the simulation clock. You can do that, but it will be code will be long. That's what I mean. Okay. I'm not saying that you have to use comparator. Again, I'm telling that if you use it, it's good for industry production level code, you'll understand more, but still you don't have to use comparators or other stuff. But I used it because, and there's something called as non-preemptive CAN algorithm. And also one comparator I use for priority here, when I wrote this code, this comparator is again for priority, the same code only, just logic. Okay, here I have some additional stuff. Don't worry about that. But yeah, but here I'm comparing priorities. The period is basically this is the main thing. So this is the comparator I wrote. Okay. So it's a priority comparator. I just put it, and a non-preemptive RM is basically, it's very easy. The same thing, simulation clock. I'm just incrementing it, and priority ready-queues. This is very easy to add. Ready-queues dot add new means it is going to be new of that priority queue, and this is I forgot the terminology here. So that this priority queue is basically the TCB. It's accepting that whole TCB object, and new of priority comparator. It looks complex actually, to be honest, but when you implement it, it is actually, you can understand this is very easy. Okay, so this is how this is again I used array list. Okay, so don't get confused with too much constructs I use, but I want to write the code. I want to learn all this. But as you do this code, this whole thing is one algorithm. See how many lines. It's actually few lines of code. It's not like 10,000 lines, or I showed you the other day for my PhD. I don't know how many lines I wrote, but these are few lines of code. So it's not complex. Is that clear? So if you want to do the project, do right away. So don't wait. If you have any questions, you come to my office. I'll help you. Today, I think I'll be there in my office from 5 o'clock to maybe until 8 o'clock. Okay. I mean, if you want to meet anytime after 5 or anything, just send me an email. So sometimes I like to work at home. Sometimes I like to work at the university. Sometimes I be here at 8 o'clock till 9 o'clock. Sometimes I go home because I'm hungry. I go home and then work from home. Okay. Is that clear? So if you have any questions, please do start immediately. Any questions? How this simulation is done? Discrete event simulation. Go ahead. You can use whatever you works for you. There's no, I cannot tell you your you write your own logic. You don't have to follow any specification. So I just gave you a template, rough template of the class diagram, what should be there, right? So whatever you find, you don't have to really follow the class diagram. You can think, and whatever I discussed, whatever way you do it, it's fine. As long as you're able to understand that discrete event simulation, how to increment the simulation clock, and how to remove the process from one queue to another queue. It can be as simple as you don't have to use priority queue, you don't have to write comparator, you don't have to do anything. You can write with the normal queue itself. It's no problem for me. Is that clear? Why I said priority queue is my code wise is very easy. I don't have to write to search the entire queue, etc., etc. So that's why. So as long as you're able to understand discrete event simulator, it's fine. And if you have questions when you're stuck, please come to my office. I'll help you. Okay, because everyone writes the code in their own way. That's what I'm telling. Is that clear? How about the students in the Zoom? Are you able to follow?
Yes, sir.
Okay, so don't because seeing my code, don't think it's complex. Actually, it's easy. It's not complex. It's easy actually. Read about comparators and how to read about priority queues in Java. It becomes a lot simpler. Have you used priority queues and comparators before or not? David is nodding his head, but how about others? But you wrote your own priority queue, right? Here the priority queue is implemented for you. In C++ or data structure course, you have to implement the priority queue. Here I'm not implementing priority queue and all. I'm using that someone has implemented, it's working fine. I'm just taking from the where is that? I'm taking from the head of the queue. See, just say ready queue dot get of 0, get of 1, so I get a 2, I don't know why, and r1 dot peak. All these things are available. So peeking into the queue is not I am writing the function, is already given by Java. So I don't write anything. But in data structure course, you'll be writing the entire code for it so that you implement this thing. But here you don't do that. Is that right? So read the priority queue. Of course, you can refer Java docs. Read the priority queues, compare, and all these things. You will be a good developer. And if you put this in GitHub, people will appreciate your work and you can get job, right? It's not just for the course I'm telling you, it's for you to get the job, right? Or if you want to do research also is good. If you want to do good research, master's, PhD, whatever. How many of you want to do PhD here? Raise your hand. Very eventually. How about you, David? How about you? You want to do PhD? Actually, your teacher doesn't pay you more. Only software pays you more. Yeah. Yeah. Yeah, exactly. I mean, of course, then high school teacher, assistant professor or professor get paid more. But when you want to go into industry, you can easily. I think my friend, I told, not my friend, my student. Okay, who is now my friend? Okay, I would say like that. So he is in Amazon, right, in this Alexa team. So he'll be getting around $300,000 per year, and I'm not making even quarter of that. I mean, so you cannot compare industry with this thing. You, of course, you make a lot of money in industry, right? My brother is almost getting 200,000. He's a data scientist, so he's getting $200,000 in Canada. I told him to do PhD, and he said, I want to earn money, and he want to buy house, and he want to get married, he want to have kids. So that's the reason he don't want to do PhD. So it's your priority in choice. Okay, so I'm not telling that you have to, but anyway, whatever you develop in this course, it will be useful for your career in whatever way it is. Okay, is that clear? Any questions, Samantha? Okay, very good. Okay, let me start the next scheduling algorithm. Then I will tell you how to modify this logic, whatever I wrote in the board. So this should be clear. So we are reading all the information from the file and putting into a queue called as arrival time queue. We can call as arrival time queue. Okay. And when you say arrival time queue, it's best you always use this camel case. I just want to stress you that when you have a variable, you always use in my code. If you see, I have been using always this camel case. Okay, arrival time priority queue. We put arrival time priority queue because if you use priority queue, put name like this arrival time priority queue. This is camel case. So use industry standards. This letter should be small, followed by capital letter here. Okay, so don't when I teach CPSC 131 here first time, in a lot of students even keep their variable name X, Y, Z, W, R, Q. I don't know what that mean actually. It has to be have meaningful variable name, right? Of course, there's nothing wrong in that, but when someone reads the code, they have to understand what that means, right? Anyway, so if you can develop this part, then shortest remaining time next will be easy to implement. First, do the shortest job first. Don't think that this question will not be asked in the interview. It's a very simple algorithm, but this is often asked in the interview. Remember that. Okay. So, and I spoke to my dad like 2 weeks before, and he told me that he was actually in charge of the IT department, like computer science. Back in 1987, he went to London to get trained, and he was using those time. It was punch cards. He was telling, and I have not seen punch cards in my life. I was not even born. So these scheduling algorithms were used those days in batch processing system. That's why in the textbook they called as scheduling in batch systems or batch processing system. So even though it is not applied now, but it was applied before in 1980s or 1970s. So punch cards, you can ask Dr. Hofmeister or Dr. Hucklin Kim. I mean, they can tell you how they work with punch cards. Right? Punch card is actually non-preemptive always, because you give to that. And if the process is going for IO, you don't preempt. It's just sitting on the CPU, it won't do anything, and wasting the CPU usage, and then you are doing that. So the preemptive, it was non-preemptive those days because they used punch cards, etc. And this is scheduling in batch operating system. But then they had this called the shortest remaining time next. Okay, this is another good algorithm, shortest remaining time. So which is in different books they call different this thing. So this is time, shortest remaining time next. So I will go with the analogy I spoke to the last class. So David, I use David as an example. So David arrives at 3 a.m. to my office. This is the motivation for this next algorithm. David arrives at 3 so not 3 a.m. sorry, 3 p.m. Okay, David arrives at 3 p.m. and Dr. Hofmeister arrives at uh, uh, 3:05 p.m. Okay, into my office. And in shortest job first, what I will do is I will continue start 3 p.m. I'll be working with David, right? I'll be working with David. So he has big question for me, whatever. So we'll be working David, working with doing. So 3:05, what happens? There is an event occurring. What is that event? Dr. Hofmeister arriving at my office is my event. This is called as a scheduling point. This event is all is called as scheduling points actually, right? See at this scheduling points, see it is 5 minutes. Okay, so he has completed 5 minutes. Now at this scheduling point, I have to make a decision. In non-preemptive case, I really don't. What non-preemptive case what I will do? Even if Dr. Hofmeister is arriving at 3:05 p.m., she may need only 1 minute, but still David is taking maybe 10 minutes, 1 hour with me. And Dr. Hofmeister has to wait for that amount of time, right? Is that clear? But now 3:05. So David completed 5 minutes of work. And Dr. Hofmeister is coming at 3:05. I'm saying, no, David is here with me. I cannot help you. Okay. I have to help David. And I keep continuing to help. And David can lead to starvation. Basically, Dr. Hofmeister will be waiting indefinitely. She doesn't know that when she will meet me. But now at the scheduling point at 3:05 p.m., I can ask David, how much time I need from still remaining for you. So he said, I need 5 more minutes. So I already completed 5 more minutes. At 3:05, I will know that I'm going to ask David how much more time he needs. He said I need 5 minutes, right? And Dr. Hofmeister is saying that I need only 2 minutes. So this scheduling point, I have to make a decision whether I have to keep continuing with David or keep continuing or switch, or can I help? Can I answer query for Dr. Hofmeister? So at this scheduling point, I will make a decision. So actually, David required total of 10 minutes of my time, right? Because 10 minutes. And I already served 5 minutes for David. But Dr. Hofmeister is coming at 3:05 p.m. And now I'm going to say remaining time is basically David needs 5 minutes. But Dr. Hofmeister is saying I need only 2 minutes. Then what I will do? I will say, David, can you please leave my office for 2 minutes? and come back. Okay, this is not exactly, maybe there may be another process which is less than that coming. Okay, I cannot say exactly 2 minutes because there may be Dr. Haklin Kim may be coming and say, Ajay, you need 1 more minute, then you will be waiting again, David, right? So I will always choose shortest remaining time next. Who is the shortest now? Whether it's David or initially it was David, but after that, who's the shortest remaining time is Dr. Hofmeister. So Dr. Hofmeister will be scheduled till 3:07 p.m. right? So she will, Dr. Hofmeister is here. And then she answers my question and goes back. Again at 3:07 p.m., I have a scheduling decision to make. Suddenly at 3:07 p.m., Dr. Haklin is coming to my office. Then who will I prefer? He is saying that I need Dr. Haklin Kim. Yeah, I will see his, I will again ask this question to him. How many minutes you need? He'll say I need only 1 minute. Then then David will be in the still in the ready queue, right? So he'll be waiting to get serviced. And this 3:07 to 3:00 p.m. I will be serving Dr. Haklin Kim. Is that correct? And here is also, if shortest job keeps coming, David can get postponed, but at least David got some of his work done, at least, right? But then if no one is arriving, then at 3:08 p.m. So 3:07 to 3:08, I think I think 3:08 till 3:08. 3:08 is my decision point, scheduling points. Then I will continue to serve David. So this is the concept behind shortest remaining time next. Basically, it is a priority-based scheduling algorithm. Again, we are looking at the CPU burst time of each of this process. But at this, we are one difference is that we are preempting the existing process. Is that clear? So that is the main difference between shortest job first and shortest remaining time next. Is this analogy is good, better? Can you understand it? Okay. We'll do with, how about Steve, who else is there? Nadisa, do you have any questions about this? Please do ask question, even if you're in the Zoom, please do ask question. I can hear you.
No, it's understandable.
Okay.
It's logical, yeah.
Okay, right. So let me give an example for you. So we have process number, right? And we have arrival times. So I'm going to give an example of shortest remaining time next. Then you can think what changes you have to make shortest job first to be preemptive in your scheduler when you write the code. Okay. So how do you update the simulation clock? Right. You have to look at the priority queue and see, who is next, and you have to compare that. Okay. Think of the logic. Okay. But anyway, let's go to arrival time is 80. And best time, execution time, CPU time, all means the same. So again, I have process 1, 2, 3, 4, 5, 6, and arrival time is 0, 1, 2, 3, 4, 5, and burst time is 7, 5, 3, 1, 2, 1. So this is the given parameters, right? For this process, this is 1. So what algorithm we are going to use? Shortest remaining time next. Now we are going to develop the Gantt chart for it. Shortest remaining time next. As the name implies, you can see that who is the shortest time remaining time next. So initially the Gantt chart will develop. So we will have this process, right? And remember that arrival time means that the process is initially, process is not actually, program is initially in the hard disk. So once it comes to the ready queue, once it comes to the RAM or ready queue in the RAM, that is considered to be the arrival time of the process. Okay, David, you have a question? I mean, I don't know. Actually, to be honest, I had to Google. So this is Gantt chart. This is how it's pronounced. Yeah. It's actually timeline, basically time telling what to go. I think it's coming from, as I said, these concepts are derived from management in systems or management information systems or management. They have job scheduling theory. So, it comes from that. So I don't know, actually, to be honest, I don't know what is, I say Gantt chart, but I don't know really. Okay. Okay. This is our scheduling timeline, which is we are going to draw a Gantt chart. So it is a time 0. Simulation clock is at time 0. Then at time 0, is any process arriving or not? Yes, is it arriving or not? Please answer me. Justin, Joshua, Josh. So what process is arriving? 1. So actually, if you draw the ready queue, what happens in the ready queue? Only ready queue process P1 is there, right? It arrives at time 0. So we remove this process and schedule that process. Schedule that process means you're going to increase the simulation clock time. But how you increase? So let's say process P1. Can you tell me how long you can schedule this? So we schedule until the very good. Next arrival time is going to be what? 1. So this 1. So this arrival at this point of 1, you have to make a decision, right? Now at I will give a tick mark. So at 1, this process arrived. Now, how much is the remaining time for how much work it has completed? This process P1. 1, right? So it has completed 1. So it will remain 6. Now, who is process P2 arrived, but who is having the smallest execution time? Is it 6? Is process P1 or it is process P2? Tell me, guys, who should I schedule next? Yeah, because P2 is having 5 units of time. By here it is having 6 units. David, or what? Sorry, not David. Process 1 is having a 6 unit because he completed only 1 unit of time, right? So the process P2 will be scheduled. Is that right? So P2 will be scheduled again for how long? Until the arrival of the next process. So when the next process arrives? Yeah. See again what happens? You are removing this, the preemptive, right? I removed it. I have shown here. So then again P2 is there. So P2 is coming a time and P2 will be there. Again, I'm just writing in P1, but it is sorted by the basically. Actually, if you use a priority queue, it will be automatically the P1 will come here and P2 will go there, right? Because no, it's P2 as actually is having the lowest. It will be P2 and P1 because P2 we had to put back into the queue. Remember that in the previous case, we don't have to put back into the queue. Now we had to put back into the queue because the process has not completed execution. So you have to insert the back, the whatever the process we are preempting, we have to insert back into the queue. And again, we are insert back by sorted by the execution time. The remaining execution time is basically in this case is going to be 6 units of time. Is that clear? So implementation wise, also think how you're going to implement that. Shortest remaining time next. So P2 will be executed till 2 time units, right? Is that clear? And at 2 time units, what is arriving? So process 3 is arriving, but how much
3.
P2 is complete? Yeah, very good. And how much is completed? This P2 is completed. This is basically 1, right? 1. So this will become 1. Is that right? And now we have to compare. Now we have three process. There is a competition now, right? P1, P2, P3, all are there in the ready queue. So if you want to draw this is also going to the ready queue. P3 is also going to be the ready queue. Again, I'm just drawing it, but it will be sorted. When you insert some element in the priority queue, it will be sorted by that. So you don't have to worry. But P3 also will be there in the ready queue, right? Because P3 is arrived at the time in 2, right? So this, if you think about so let's even not think about a priority queue. If you think about the queue, will be adding that process into the queue, right? P3. Now there are 3 processes. So which process will get the CPU now? 6, 4 and 3. Which was the shortest execution time? P3. Is that right? So P3 will be there. And how long should I increase the simulation clock to till what point of time? 4, right? I make. So I think P1, P2. So P2 is okay. 2 to, did I make any mistakes? So 2 to 3 is P3, and 3. What happens is that it is P4 is coming. Is that right? So P4 is coming. So P4 is also coming. You put in the queue here, and again we have to examine this queue and see which is the shortest. So now this has completed 1 time unit. So basically this will become 3. You can strike and you can write that as a 2, right? And there is P2, P3, P4. Right, this is also there in the ready queue. All these processes, none of these processes completed. So all these processes are basically in the ready queue. Now which process has the lowest execution time? Smallest execution time is what? How much is which? 4, right? So process 4 will be scheduled. For how long it will be scheduled? Next process arrives at 5. No, 4, right? Yeah, 4. Yes. And then what happens? This process 4. Now, please note this point. So process 4 has completed one time unit, so it becomes 0, right? So this process is basically exiting out of the RAM. So we don't have to put this process back into the queue at all because the process is complete execution. So now we have competition only between P4 is got 1 unit and it is just going out. Now there is no competition. Like there is no competition. I'll erase this. So there is no competition because this is not there in the. It is totally eliminated from the ready queue. Basically, it has completed everything, right? And now at 4th time unit, then process P5 arrives, and P5 arrives, and which now tell me which process I have to schedule. Which is having lowest execution time? Please watch this carefully. This point, Josh. So which one I should schedule? Because 7, 4, 2, and 5, 2. So there is Samantha. Yes, that's a very good assumption. Okay, there's a tie breaking. You have to break the tie. Because 2 people are coming. I have to toss a coin. I cannot toss the coin and select. Of course, you can select tossing a coin though. But if this is one good strategy, whoever has arrived first, because now there is a tie between what? P3 and P5. Is that clear? Do you see that there is a tie between P3 and P5? See, here people have proposed several things how to choose between. Again, if you read research papers vast, how do I choose P3 between P3 and P5 have the same arrival time? One solution is that look at the process who arrived first, that process will be served. That is a good assumption to have. Is that clear? But need not be. You can also ignore the assumption. Maybe you can toss a coin and then see which one you want to schedule. That's also possible. Your implementation wise, whatever you think is correct, you can do it. Why I want to choose process? What is the logic in taking process 3, Samantha? Can you explain a little bit more? He has arrived first. So what is the other logic you want to say? So if you choose P3, what is going to happen? Yeah, that's right. That's right. But can you tell me any advantage of why you choose P3? Any advantage? It is going to reduce what? The turnaround time for the process P3. Is that right? Thinking logically, because it has arrived first. So if it leaves soon, it's good, right? I don't want that process to stay in the RAM for so long time. So if you say the shortest, when there is a tie, you can say that I want to choose the process which has arrived first, which is in this case P3. If you do that, what you're going to do is that you're reducing the turnaround time of that process P3. Is that right? Otherwise, the process P3 has to wait for a long time. So that is if you are going to write a paper, means of course people have already proposed it. But if you're saying that that's such a tie you want to break with arrival time, then you have to give a reasoning. The reasoning might be this way. So the process who arrive first will be scheduled because we can reduce the turnaround time of that particular process, which means that I can reduce the average turnaround time of all the process also, right? So is that clear, Josh? So what this is a very good strategy that what Samantha told is to choose P3 because it arrived first. And how long it will run? Yeah, until the next process, which is nothing but P5 is arriving, right? So P4 is not, it's totally gone. So now this one is basically 1. Is that clear? So this will become 1. Now again the tie is happening because the P6 is arrived. Again we can say that did I miss something, or did I write anything incorrect? So P3 is there. Sorry, I didn't make a mistake. Is that right? So P3 is scheduled. See, while explaining, I get confused. So P3 will be scheduled till 5, and here it will be nothing but I can strike this off. This will become 1, right? Right. And now we have competition at 5. All the processes have arrived actually. So will I choose P3 or P6 in this case now? Again, it's going to be arrival time. So P3, is that right? So P3 will be continuing to execute. So P3 will be continuing to execute till 6, right? And so that means that P3 is will become what? It will become, I use different colors. This will, I use red color, I strike this off, and that will become 0. So basically what P3 will be basically gone forever, right? Gone forever. Is that correct? Because here it completed 2 units, and here it's completed 1 unit. So basically 3 units has been completed if you look at the Gantt chart, right? Is this clear? And at 6, what happens? Now all processes arrived, right? Now all processes arrived. I put it the green stick mark. All processes arrived. I mean, of course, process keeps arriving, but in our assume that all processes arrived. In our on our list of 6 processes, all processes arrived. Go ahead. Yes, that's what I want to tell. Actually, that's the point I want to make. You told the answer actually. So all the processes arrived first. Sorry, all the processes are not first. All the processes arrived in the RAM. See, at 6 unit, all the processes arrived, right? So basically, so among that, which is the shortest process? Because these 2 are eliminated. So which is the shortest one is basically P6, process 6, and it will execute till 1 time unit, right? So P6. See, now the thing is that when all the processes are arrived in the RAM, shortest job remaining time next, or shortest job, shortest remaining time next, or shortest job remaining time next, whatever, it is going to behave exactly like shortest job first. From the point all the processes are in the RAM, because you take this analogy, right? So again, say V6 P6 scheduled, and that is going to become 0. So it is striking 0. Again, we are going to compare 6, 4. This again, which is the shortest job? It is between these 2. It is going to be 5 is still there, right? So which is the shortest job? P5, right? So P5 will run, but P5 will run, and all the processes have arrived actually. So 2 is the lowest one, right? So 2 will become 1, and 1 will become 0, because this is the lowest one. So the shortest job first is going, shortest remaining time next will behave exactly like shortest job first after all the processes have arrived in the RAM, because this is a job which is slowest remaining time, because every time it keeps decreasing, its number is going to is going to get low and low, right? So the burst time is getting low and low. So basically you can say that P5 will be scheduled from 7 to 9 units, right? It requires 9 units. So 7, 8, and 9. And you can remove this because this becomes 0. And now among these, what is now, which of the processes there still in the RAM? It is P2 and P1. Among that, which one will choose? Yeah. And how long will, yeah, P2, is that right? P3 is still there or not there? P5, according to me, and P2 already, P3 is left, right? Only P2 and P1 are there. These 2 are there, right? So among these, which one is shortest?
P2.
P2. So P2 will go, so this is P5, so this will be P2. Again, P2, see, you don't have to check because there is no process in the, there's no process arriving. Basically, what you can increment until 13. And because every time you decrease by 1, this is going to be the shortest job, right? So, and then finally, it is going to be P1, and P1 is going to execute from 13 plus 6 is 19. Are you understanding this? Shortest remaining time next. So then you want to have a small implementation. So first implement the shortest job first for your programming assignment. I still didn't know who is doing the programming assignment. Maybe we'll collect the information next class. Okay, next class tell me who is doing the programming assignment. But I just want to make sure that you understand this clearly. Right? Implementing code is fun. Yeah. I tell to my students always, coding is like an addiction. It's like an addiction to alcohol, whatever. Coding is also an addiction. If I start to code, I will keep coding, I will never end. It's like watching, what is it called? Watching a series, TV series. Have you watched Money Heist? Money Heist? Yeah. Yeah. Money Heist or Prison Break, season 1, season 2. I was, what is it called? There is a term, watching, eating and watching, Huh? Binge watching. Okay. Yeah, whatever. Yeah. So I used to watch the Prison Break like I didn't sleep at all. Even I don't want to sleep. Every episode ends with the next question or what's going to happen. And I keep watching. Like I watched Prison Break season 1, 2, 3 completely in 1 week without any break. So that is how addiction can become. So programming is also an addiction. Once you start to fell in love with coding, you will not leave coding. You will like to code and you want to code different things. So coding is an addictive thing. Okay, it's I don't know. Too much addiction is also not good, but because if you are family members, you have to spend time with family, etc. Right? And yeah, the coding is an addiction. Remember that. So when you implement this, you will just use normal queue. Then you will see okay, priority is much better. You implement that, and then you want to implement that. And there's one algorithm which is called as longest job scheduling algorithm. I don't know why the scheduling algorithm exists in the first place. Longest job scheduling algorithm. I'm not lying. You can Google about it. Let me Google. I'm not lying. So there should be longest job. Oh, 1 minute. Why this coming pops up? So you can propose on this is a longest job scheduling, longest job for scheduling algorithm. So there's an algorithm called longest job. I don't want to explain longest job scheduling algorithm is exact opposite of shortest job. Okay, you're going to choose longest job scheduling algorithm. Is a non-preemptive algorithm again. And then if there's a longest job scheduling algorithm, then of course longest job, shortest long, I don't know how to call, shortest remaining time, like there is a similar thing, longest remaining time next algorithm. So there is algorithm people are proposing. I don't know whether they are useful or not, but they keep proposing. Okay, but the longest job will always suffer from turnaround time is going to be more, response time is going to be more, everything is going to be more in that longest job scheduling algorithm. And so there is also people have proposed longest job schedule. If you want to implement for fun, you can implement. Okay, because there's small modification. Instead of selecting the shortest job, your priority will be ordered by different way, right? That's the only small modification you have to do to implement this algorithm. Is that right? I'm not going to explain longest job. Don't make me to explain. It's not quite useful algorithm. Okay. How? What do you think, Zoom students? Zoom? Nadia? Narisa? Nadia or Narisa? I actually forgot. You said that one time I can call you Nadia.
It's both. Yeah.
Both. Actually, Nadia is an Indian name, actually, Nadia. So there are people which name, there's a very famous actress back in 1980s. Her name is Nadia. So I used to, yeah, her name is Nadia. Nadia something, yeah, Nadia. Okay, so this is the, so I just wanted to make a point here. So please don't forget this. In case all processes have arrived, to the ready queue or in the RAM, you can say ready queue is, where is ready queue? Ready queue is in the RAM only, right? So ready queue or RAM, SRTF, shortest remaining time next, or shortest remaining time first, or whatever you call, will behave like exactly like shortest job first. Is this clear? This point clear, right? Okay. Next we'll go to the next time. So another thing is that, of course, I didn't calculate this turnaround time, etc. Maybe I should calculate for you, or you can do. You know how to we did, right? So I mean, this basic math. I'm going to have assignments on completion time. What is completion time? Completion time is what is turnaround time? Completion time minus this arrival time is called as a turnaround time. You can calculate, and then you can calculate. Once you calculate turnaround time, you can know how to calculate wait time. What is the wait time? I told you how long it's waiting in the ready queue is nothing but wait time. So the wait time is going to increase, or you can calculate and see the wait time. So wait time on the formula, how so turnaround time is nothing but is another way of writing is burst time plus IO time plus because IO time is basically 0. We will have an assumption when IO time is not 0 also. But right now IO time is 0. We can eliminate this, and then we have bus time, IO time, and then what else? Wait time, right? So you can calculate this. Basically, we know what is turnaround time from another formula, which is nothing but completion time minus arrival time. So then what is going to be the wait time? Wait time, you know what is turnaround time. So wait time is nothing but T turnaround time minus burst time. That is going to be the wait time. Okay, WT means wait time. Is that clear? So you can calculate all these times basically for this process. And one more important thing is that you have to go from the right to left to calculate the turnaround time for the preemptive scheduling algorithm. You cannot go from left to right. In the shortest job first, you will go from left to right. In the Gantt chart, you have to go from right to left because here process P1 is completing at 19th time unit. So this is the time. Okay, if you go from left to right, you will see that it is completing at 1. No, it is not completing at 1. It is completing at 11. So completion time is basically P1 is completing at 19 time units, and P2 is completing on 13 time units, and I go from right to left, and P5 is completing basically at 9 time units, and P6 is completing as 6 time units, and P6 is complete. No, P6 is completing at 7 time units, right? And P3 is completing at 6 time units, and P2 is completing at P2 I already wrote, right? So P1, P6. So you can look this thing, and P1, I think P4. P4 I didn't write. P4 I had to scan here, and it's completing at 4 time units. So you scan this Gantt chart from right to left to know the when it completed, not because it's a preemptive scheduling algorithm. Is that clear? Okay, go ahead. Because we have one CPU. This is uniprocessor scheduling. And multiprocessor scheduling is again NP hard problem. So, I mean, of course, now we cannot find an optimal solution. There's no way to prove that, because it's characteristics of the task, and it is non-polynomial time, NP hard actually, because you cannot find a correct, you cannot prove it actually. They use heuristic approaches. It's called bin packing problems. You can research on bin packing problems when you have multi-core processor scheduling. So they have gang scheduling, several scheduling are there, but no one can prove that their algorithm is the best algorithm. Okay, so it's bin packing. Bin pack. You can learn what is bin packing algorithm. Just Google that, and same thing will apply to multiprocessor. Here is imagine that there is one supermarket, which one counter, one cashier, one till counter, one cashier, and everyone has to be served by the one person. Okay. If you have multiple counters, that's like multiple processors, right? Then it's going to multiprocess scheduling. Does this make sense? Okay. So this is all called uniprocessor scheduling because we have only single processor. And these things were in use before, not now, because now we have multi-core and everything, and now we are round robin. We are going to talk about round robin. Before I talk about round robin, let me talk another algorithm which is called a first come first serve. We can complete this algorithm, first come first serve. As the name implies, is like FIFO queue, right? The process has the least arrival time will be scheduled first. Yeah, the process with least arrival time will be scheduled first. This will be the shortest path definition. Again, it is a non-preemptive algorithm. So once that gets the CPU, this is similar to a normal queue. In a supermarket, you go, there's only one cashier, only one till is open, one counter is open, and you cannot kick other person out because still he is checking. That's the thing I always keep checking from the one counter to another counter. I make a round, checking which counter has, someone buying 4 or 5 cans of milk bottle and so much things, and I have to wait for a long time for them to check out, and only can go. So that's why I scan all the queues and see which one has less number of people with less number of less items to check out. Then I join that queue basically. So because we cannot preempt the person, right? Once you start the billing, you cannot preempt the person in real life, right? You cannot say that, oh, this guy has less, you come back and next You cannot ask them to make in a round robin way. You cannot do that. So this is going to be first come first serve, which is normal. Bus waiting in the queue for the bus, or waiting in the airport, waiting in the checking the thing of luggage in the airport. All comes first come first serve, right? Maybe there is a priority boarding. If you are a rich and you are a first class passenger, then you are given like treated like a royal king or whatever, right? So that is going to be. I wish one day I will become like that. I go in first class. My dream. Business class. I never travel in business class in my life. I always travel economy. That too not premium economy. There is something called premium economy, which has more leg space. I don't travel in that. I have never traveled in that also. And it is a non-priority based scheduling algorithm. See, some people can argue with this when the interviewer asking why it's non-preemptive based algorithm. You can tell that sometimes people say, okay, arrival time is the less, so we are basically based on the arrival time, we are giving the priority. You can say like that, right? Because whoever comes first, that arrival time is less, we are giving priority to them. But actually, if you argue in that way, then you can say it is a priority based scheduling algorithm. But usually this arrival time of a process is actually not a characteristics of the process. It is not an attribute of the process. We don't know when it will come to that RAM. But other thing like shortest job, execution time, those are the characteristics that are inbuilt in the process, right? So that is the priority base. So here they usually call it a non-priority, non-priority, non-preemptive, and I wrote 2 times. Sorry, this is a non-priority based. It's not a priority based algorithm. That's what I'm telling. But you can argue with me that it is a priority. In fact, you're choosing the process with the least arrival time. But actually, arrival time is not the property of the process. It is you cannot say for that reason it is this one. Okay. So this also interview you can also argue, why you call, you can argue in the interview. People, we don't think that these things are not asked in the interview. It is asked still in the interview. First come, first served. Real life application, waiting for the forming the queue, getting into the bus or whatever. In India, it happens other way. No one follows any queue. Just jump in. Too crowdedness, right? Overcrowdedness. That's the John Conway's way of life. If it's too overcrowdedness, you die of overcrowdedness. If you're lonely, you'll die of loneliness. John Conway's way of life is there. You can simulate that. Write code for that. But that's not a part of this course, so don't worry. But there's called as John Conway's way of life. Okay, you can Google about that. Anyway, so I think I still have 5 more minutes. I can schedule this for you very soon, so I can complete this algorithm. I have a satisfaction that I completed a few algorithms today. Arrival time and bus time. See, I can keep talking for whole semester about the different scheduling algorithms, reading the research papers and why they go from one algorithm to another algorithm. But if you understand the basic algorithm, other algorithms are very easy to understand. Right? So here, here we have, so according to first scheduler is starting from 0, right? 0. And who arrives at the time unit 0? It is basically process 1. And how long it will be scheduled? Till 4. So 4. So process 1 will be scheduled till 4. And then who is coming next? Of course, until this all processes arrived. Actually, arrival time, all the processes arrived here, right? But who has the least arrival time? Is basically P2. So P2 will be scheduled until what time? C is burst time is 3, right? It's 7, yeah. And at 7, I have to make a decision, and all the processes are on the ready queue. Who has arrived first? It is process P3, so it is going to be P3, and it's going to be scheduled till 8. And P4 is arriving next, and it has till 10, and P5 is basically till 15. There's nothing big deal about this algorithm. Basically, whoever arrives first is given the process is non-preemptive. Is this clear? Go ahead. That's actually burst time. I think I wrote it incorrectly. For process 3, yeah, it is the 1. Actually, not 4. It's 1. Okay, sorry about my handwriting. But what is the problem with this? Tell me what is the problem. This happens always in the when I fly in aircraft, not aircraft, when I check in my luggage in the airline counter, I get really this first come first serve. I don't like, because someone is checking with whole family coming with 3-4 kids and checking their luggage and checking for everyone. I am single person and I have to wait for them to complete. So that means that it is what is the problem with this algorithm? It's going to lead to, yeah, it's going to lead to high turnaround time. What is the problem with shortest job first? So this is leading to, no, it won't lead to starvation. First come first serve, there is not starvation, because it's coming, what is it? Yeah, that is short starvation. Here it is called as convoy effect. Is it, did I tell you right? The other day we spoke, right, David? Convoy, or how do you pronounce this? Can anyone? Yeah, convoy effect. So this leads to a problem called as convoy effect. What is convoy effect? Like, as I said, one by one coming, and one person is checking the luggage and he's taking half an hour to check in luggage. My flight is like immediate. I still have to be waiting in the queue. And I need only 2 minutes of time, but these people may not have documents properly, whatever, passport verification, all these, every 5 people, 6 people checking as a member. That's why you have to go for premium boarding, I think, and you need to have some more money for that. Anyway, so the problem is that it is going to lead to convoy effect, basically, in which shortest job will have to wait for the longest job to complete. And this is going to be, happens for, but longer job is happy, but shorter job is not happy, because shorter job, see, I need only 2 minutes, I have to wait for 1 hour for you to meet. This is really annoying, right? So that's why first come first serve is a problem. So we can address this first come first serve problem, okay, with another algorithm which I'm going to see in Thursday's class, that is called as round robin algorithm. Okay, we are going to address this. We don't want this convoy effect, okay, and we don't also want to have shortage of starvation problem. So we want to avoid those two things, but it will lead to other problems, but let's say discuss but later. But round robin is used in most of the computers these days. Okay, for time sharing environment, it's sharing the time of the CPU is called as time sharing, and we will see about round robin in the next class. Is that clear? I hope you got information what you need. I upload the videos that I taught in the previous semester. You can watch those videos as well. Okay. All right. Thank you, guys. Have a nice day.
Thank you so much, Jay.
Thank you, Nadia. All right. Amen. Steve, bye. Yeah.